Greetings. So cryptography, and our first part is about rather simple cryptographical systems. So the first one I wanted to do was number 8. That was on a cipher key, and it is basically how to attack, just to show you that it is actually something you can easily attack. So number 8, that is, so we are dealing here with this guy here. Okay, this is our text. And the way that we attack this is by counting the frequency of letters. And we see rather frequent letters are K's, 1, 2, 3, 4 times K, but V I think is even more frequent. 1, 2, 3, 4, 5, 6. So I have a lot of V's here, especially these here. Double things often means it's a vowel at least, and so we expect this to be a vowel. There's other things you can do, right? Analysis of words, we know that where vowels and consonants can be and so on. All right, so I'm gonna make the suggestion that, and I'm using an orange. Orange is, for me, the encoded message, and black is the actual value. So I'm thinking, so based upon, I'm not gonna write it down, based upon frequency analysis, I think that V is E. So now we have to know what is V and what is the shift that happens, right? So what is the value of E? Well, that's I have here an alphabet, and there's a reason I have this way. But it also allows me quickly to calculate all the values here: 3, 4, 5, 6, 7, 8, 9, 10, 11. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25. You know that it's the last one. Okay, so V is 21 and E is 4. So that is 4, and the value that we have calculated is 21. So now think, it is the black is the original, and you're making it into a red and orange one by adding a certain amount, and what we add here is 17. So our encryption key, so to go to there, from there to there, that is, we added 17, so we think that our encryption key is 17. So that's a guess. And once we have decided what our encryption key is, we know also what our decryption key is, and that is subtracting 17. Okay, so this is of course always modulo 26. So to decrypt is minus 17, but you know, you can also think it is as 9 mod 26. So instead of subtracting 17, I can also add 9, which is slightly simpler, right? So I don't know, let's try to decipher now what is D. So we have the first word. Let me copy the first word, DVE. Okay, we have already guessed. We'll see whether this mix is correct, right? But worst case scenario, you have to do this 26 times. D, so D, we have to remember decrypt is we're gonna add 9 to it. So when we are at D, which is 3, we're gonna go 9 higher, 12. So this would be an M. So D would correspond to M. And E has value 4, and if we decrypt it, we add 9 to it, or subtract 17. If you don't like to add, subtract 17, but 4 minus 17 is minus 13, which is the same as 13 mod 26. Okay, so both cases leads us to 13 here, which is N. Man. Well, that's an English word, so that looks good. CFMV. CMFV. Well, V we said is E. So that one we don't have to think about. C, we have to add 9 to it. So C is 2, add 9 is 11. That gives me an L. M, I'll do this a little bit slower in case you can follow. M has value 12, add 9 to it, it gives me value 21, so this would be a V. That doesn't sound correct. Let's double check. 12, and if I add 9 to it, I get 21, that is a V. Did I make a mistake then with the C? Right, let's see. C was 2, add 9 to it is 11. No, so that doesn't make sense. C, and that would be then M is a V. Oh, I see what I did. It is CFMV and not so. Okay, this is so that this is M, which is therefore V. Okay, so now I see a bit better what's going on, right? So I swapped these two letters. Sorry. So this was an F, and this was an M, and this was a V. CFMV. So M was V. What is F? F has value 5, and add 9 to it is 14, which is an O, which we kind of were guessing now, right? It's an O. Okay, so the next one, KF. Let me write KF again. KF. We don't need to redo F anymore. We know that it's O. But K we haven't done, so K has value, so looking at our table, K is 10, adding 9 to it is 19. So K becomes T, which is something you might have already guessed, love 2. Okay. Then the next word is NFEUVI. Okay, I'll copy it one more time. NFEUVI. But I want to show you this thing here. We're going to use it also to decipher what we call the next question, the next problem. So what this does is it actually has shifted the alphabet, right? So so in other words, if you have a shift of 0, of course, then you still have the original one. So that the first column is nothing shifting. The second column is shifted by 1, by 2, by 3, by 4, by 5, by 6, by 7, by 8, by 9. So this is the shift that we are doing now to decode, right? So let me highlight that shift. And now we can do much quicker, right? So I'm going to do it a little bit, get myself a little bit quicker here. So what we now do is just, let's see. An N, well, that is a W. F is an O. E is an N. U is a D. V corresponds to E. And I corresponds to R. So men love to wonder, and we see that there is a text coming up, and it makes a lot of sense. So let me undo it. Oh, I shouldn't have done my numbering. Now, so what I'm showing is that it's somehow cheating. We're not using congruences anymore. We're not adding anything anymore. We're just carrying out a shift, okay, by doing this. But what we actually really do is, of course, just emphasize each time. So the next word that we have to decode, let me write it up. ROU, R-E-U. The way to do it is you take the value of R, which is 17, add 9 to it, that's 26, which is 0, which is an A. So this, we know, becomes A. But using this table, we can see it much quicker. I should not use, let me use this. No, I don't want these little balls because they're making it so, okay. No, that is way too, sorry. Why is this so small? Okay. So EU, that is ND, and, love to wonder, and. So the next word was kirk with a Y. So kirk with a Y is T H A T, that, and that. The next word is zj. Z is I and J is S, and that is, okay, we could have guessed that. Then is KYV. K was a T, right? K was T, Y is H, and V is E. And that is the JVVU. J is S, V is E, that's where we started from, and VVU, and that is the seed. VVU, FW, F is an O, W is an F, that is the seed of, okay, we can, of, and now comes, I guess I have to write it down because it's a little bit too long. It's J, wait, I have to, J, T, Z, V, E, T, V, okay. J, S, T, C, Z is I, is this, and that is the seed of S, C, I, V, what was an E, we know that, E, we already know that's an N, T, do we have a T already? No, but well, let's see what T is C, oh yeah, right, we did it there, and then V is, and that is the seed of science, okay, so that's how it works. All right, so that was number 8. Now you see it is easy to crack, that we basically cracked a code, right? So here is a code that is more, how to say, considered more secure, although it can be cracked. And so this is what question number 18 is about, and this is what is normally called the Vinière. That's how you pronounce this, Vinière key. It's a French name, and there's no S here, sorry, but there is this weird accent here. No, I even wrote it wrong. Sorry, I wrote it wrong. Let me rewrite it. It's the Vigenère. Sorry, I pronounced it even wrong. Vigenère. So there's the French pronunciation. The accent on the E makes it an Vigenère. The last E you don't pronounce. The middle E you don't really pronounce either. So Vigenère, which was a Frenchman, but it's the encryption method is called Vigenère cipher, but it actually is not his. It was already known way before this. There's a very interesting article on Wikipedia on this cipher. What was not used that much, but it was interesting. Also, an interesting connection here is that it was when Vigenère came up with describing the ciphers as in the 18th century, but it was much 19th century, but it was much before, from the 15th century, by Italians and so. It was a challenge to solve it, and Babbage, and perhaps you will encounter the name elsewhere. Babbage is somehow the father of computers, right? He was the one that first started thinking about computers and so on. So he was very much engaged in trying to decipher this, and he challenged them, and they could decipher it. So, and there's a very interesting description at Wikipedia how this works to decipher. But let's more think about how to encode the message, right? So it has a key. So the encoding key here is blue. Now, what does that mean? What are we going to do? So we have a text, and so this text is snowfall, and we have to encode this. Okay, so in a shift cipher, we would use this table here, but using a fixed. In other words, we would use a fixed column here, right? So we would, for instance, if you shift by 9, we would snowfall. So S would become B, and N would become W, etc. Okay, I'm just giving some example. If the shift was 9. But that is very vulnerable to frequency attacks. So what one does is uses a code word to change each time the shift that you use. So every letter, depending on where it is inside the string or inside of your sentence or message, gets a different encoding, and that is governed by the key blue. So what you basically do is the following. You take, I'll write the key in blue because it's blue, right? You write blue underneath of it, and if you're done, you keep writing it again. And here in this case, it just fits. Okay. And what we now basically do is add them. So remember, S actually corresponds to. I erased a little bit here my numbers: 19, 20, 21, 22, 23. So S is 18, and B is B is 1, so it will become 19. Okay, so we would make this into T because we shift once. Now, what is this table? Because if you look at it, it's called the Vigenère table. I actually got it from the article from Wikipedia. What it does is say, okay, you are using the letter B, okay? So you're adding B to S, and the result is T. Now, remember the next letter that we're going to do from snowfall, the next one is N, and the next letter in blue is L. So in other words, we're using the letters B, L, U, and E in sequence to shift. And so we alternate the shifts. That's basically what we do. So perhaps make it a little bit clear here. I'll make these. So B, L, U, and E are going to be the 4 columns in which we're going to shift. So I'll make them, count them down, that we can follow what happens. Okay, so snowfall. So I'm going to do this up here because otherwise I'm getting out of it. So snowfall, right? So how does it work? We take S, we look at S, and use the first of our keys, blue. Remember, this is how I wrote. Well, perhaps it's perhaps better to do it this way. Let me do this over here. So let me get a little bit out of space here. So we have snowball, and then we have our shifting. We alternate these key blue, but you see it's only every 4 we get we use the same affine cipher. There's just 4 different ones. Okay, and so okay, what does that do? So okay, let's now do the encoding. So S under blue under the B becomes T. That's what we said already. Okay, so that is T. N under L. Now we use this L, and we look where is N. Well, that corresponds to a Y. You understand? L. This is the code, the letter that I'm using for the current cipher. That is an L, and the letter I want to encode is the N, so it becomes a Y. Okay, so this is Y. O. Now I have to use the code for U, so I'm looking in this column, and O is I. W, but using the E key. So now I'm using this key, and W, so here we are here, right? So this is where I'm looking, that is an A. And now see what has happened in this, no, this is not what I wanted to show. Okay, no, let me keep going. B. This B here, now in this B, you have to use the code, the shift by B again. So B shifted by B becomes a C. A shifted by L becomes an L. That's of course a bit of a problem, right? A's are shifted by the letters of themselves, because remember, what we really do, if you want to do this in terms of congruences, what we really do is, well, this particular case, L has values 0, 1, 2, we also write the values here, 5, 6, 7, 8, 9, 10, 11, okay? Let's do the next one. We don't use the letter L, and we use U, which is 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 is the shift, the cipher, the shift that we use 20, and we do that to the value of L, because this is what we want to do. We're here, right? So L has code, the L is code 11, so this should be 31, but modulo 26, that is 5. Okay, so which should be an F. Let's see, is this what we get? L is exactly here what we get, an F. This table has already done the shift for us, so we don't have to calculate these things anymore. That's what it means. And you see, it shifts things. If like here, once you get to Z, it shifts to A, right? It's really a cyclic shift. Okay, so that is what was now. I forgot now what that was. So I was doing L using U. That was an F. Okay, so it's an F. But now here's perhaps my point that I want to make. See, in a regular cipher, a fine cipher, the Caesar cipher, every letter would get substituted of your original message gets the same coded value F. But this is not the case anymore, because although this is the same letter, it is encoded by a different shift, namely the shift by 4. So in that case, L becomes a P. Okay. So let's look at the here. If we would do, okay, this is just one word, so we cannot crack it just based on this one word. But you can imagine if you have now a whole sentence and you do the same trick, that the frequency of E will be hidden, because one times E is used using the L key, is shifted by L, the other time the E is going to shift by B, and so on. So this makes it less vulnerable to attack. And in fact, the way to attack it is if once you know the length of the key, then you can do this analysis again, because you say, okay, I'm looking at, so if I know the key has length 4 without knowing what the actual key is, I know that S and B, so that this T and this C come from the same affine cipher. So I split the message in 4 parts and analyze in each part what is the most frequent letter and say that is the E, and so that's the shift I'm going to use. Okay, so that makes it more vulnerable, because if you know the length of this key. Sometimes people use a variation of this is in fact not to use a key of finite length, but for instance to use a book, and so you have a message that you want to encode, and here underneath of that you write let's say you take your favorite Shakespeare or something, or copy of or Bible, say, and you look at page, you agree which page you use, and you start writing down the letters of that page underneath and use that as your shift, and this is the table that you use to encode and now also decode, right? So the decoding, how does that go? Well, once you know that the shift is blue, you do the opposite, right? So now you know that B, so let's just, if you have a T here, you look under the B, what is the T corresponds to? Well, it corresponds to an S. And let's, for instance, find what this A, let's reconstruct that this is a W, because this A has been used, we used key E for it, so under E we use where A is, yes, we find A here, and we say, oh, this was originally a W, and that's how you decode it. So this is a very nice little scheme. That is why it's actually very practical to do this in the old days, when we didn't have computers, of course, right? And in fact, in Wikipedia you find little tools that you can use to shift things and do this very quickly in the army. This is for used on the army when you would send an encrypted message to your commander without the enemy knowing what's going on. So you use the encryption keys and so on and forth. So that's this is what I wanted to say about and this Vignere key. I'm gonna use it in the next lecture. Well, you'll see it. I have used it already. So I wanted to give you a bit more background on it.